The sun is burning right now, quietly, steadily, with the same patience it has held for 4.6 billion years. Deep inside its core, hydrogen atoms drift close enough to fuse, releasing light that will take thousands of centuries to reach the surface, and only then begin its 8-minute journey to Earth. It is a slow miracle of physics, a furnace held in balance by gravity and heat, a star that has shaped every breath you have ever taken. Yet even this brilliance is not eternal. One day, the fuel will thin, the balance will shift, and the sun will begin its long transformation into something new. Before we drift into that story, if this quiet journey brings you a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps this small corner of the cosmos keep glowing, and your presence truly means more than you know. Now we drift into part 1. Part 1. What does it mean for a star to run out of fuel? When we say that the sun will run out of fuel, it conjures images of a flame sputtering out, a light going dim. But stars don't fade that way. Their fuel is not fire, but fusion, the quiet merging of hydrogen into helium deep in their cores. As long as this process continues, the sun shines with perfect balance. And yet, every second, millions of tons of hydrogen disappear into heat and light. The question is not if this supply will change, but when the balance that holds the star together will begin to unravel. To understand what running out of fuel truly means for a star, you have to imagine the forces at work inside it. Gravity is always trying to pull the sun inward, drawing every atom toward the center. Fusion, meanwhile, pushes outward, filling the star with pressure created by energy. These two forces, opposite but equal, create a perfect equilibrium, a cosmic truce that is held steady for more than 4 billion years. This balance is delicate but enormously powerful. Deep in the sun's core, temperatures reach around 15 million degrees Celsius. At that heat, hydrogen stops behaving like the gentle gas we know on Earth. Its atoms are stripped to bare nuclei, crushed together so tightly that they merge. Each fusion event releases a tiny spark of energy, and together, these sparks build the sunlight that warms our world. The sun contains so much hydrogen that this process can continue for billions of years. But hydrogen is not replenished. There is no way for the sun to create more. It can only transform what it has, turning the simplest element in the universe into something heavier, something less useful for keeping the star stable. Little by little, helium accumulates in the sun's core. It is the ash of the sun's fire, and though it seems harmless, it slowly changes the balance inside the star. As helium builds up, it begins to settle into the very center, forming a dense, unmoving core. Hydrogen, which once filled that space, finds itself pushed outward into a shell surrounding the helium. Fusion continues, but now it happens farther from the sun's center. The consequences are subtle at first, slight shifts in temperature, slight changes in brightness, but over millions of years, these changes intensify. The sun brightens as it ages. This is one of the quiet truths of stellar evolution. As the helium core grows, gravity compresses it more tightly, heating it further. The hotter core causes the surrounding hydrogen shell to fuse more rapidly. And as fusion accelerates, the sun shines more intensely. This aging process is slow, so slow that no human lifetime could measure it directly. Yet astronomers can trace it in the fossil record of Earth, ancient rocks and atmospheric clues that tell us the sun was once dimmer, gentler, cooler. This brightening is a sign, not of imminent collapse, but of change. It tells us that the sun is no longer in the same state it once was. Its equilibrium is shifting, its balance is beginning to lean. When the sun runs out of fuel, it does not suddenly go dark. Instead, the center of the star changes character. The pure hydrogen that once sustained fusion is gone from the very heart, replaced by helium that cannot fuse under current conditions. The sun still glows, but now the core contracts under gravity's relentless pull. As it collapses inward, the temperature rises further, making the outer layers swell. Running out of fuel means the death of the sun's first life phase. It is not the end of its light, but the end of its stability. Stars are not delicate. They resist change for as long as physics allows. But once the hydrogen at the core is gone, nothing can restore the old balance. Gravity tightens its grip, and the star's structure adapts in dramatic ways. The sun becomes hotter at its center, cooler at its surface. It becomes larger, more luminous, and more unstable. The phase we call the main sequence, the peaceful middle age of a star's life, comes to a close. This is not a sudden shift. It is a slow, flowing transformation unfolding over millions of years. In human terms, it is a lifetime beyond imagining. In cosmic terms, it is the natural rhythm of every star of the sun's class. So what does running out of fuel truly mean? It means the sun cannot hold itself together in the same way anymore. It means the hydrogen fusion that once kept gravity at bay no longer happens where it must. It means that the core, left without fuel, contracts until temperatures rise enough to ignite new processes. And eventually, it means that the sun will expand so dramatically that its entire character changes. But here is something gentle, something strangely comforting. Stars do not fear this change. They follow it. They are bound to it by the laws of physics, the same laws that allow atoms to exist, planets to form, and galaxies to spin. A star's life is a story of balance, loss, adaptation, and rebirth, just as much as its death is a final cooling of embers. The sun has enough hydrogen left to remain stable for billions of years. It is not a flame flickering low. It is a steady fusion engine still in its prime. Yet when astronomers speak of it running out, they are acknowledging the quiet processes already underway, the slow accumulation of helium, the gradual brightening, the shifts in energy deep within. To run out is not to fail. It is to reach the point where one chapter ends and the next begins. When the sun's hydrogen becomes too scarce to support stable fusion at its core, the second chapter of its life will start. Gravity will compress the core further, fusion will move outward, and the sun's outer layers will expand in response, transforming it into a red giant. But that is a story for another part of this journey. For now, it is enough to understand the truth behind the phrase. A star runs out of fuel not by going dark, but by changing shape. It runs out when its core becomes something new. It runs out when gravity and pressure shift their balance. It runs out when the quiet rhythm of fusion can no longer continue where it once did. And as we drift deeper into this tale of stellar life, one question remains. If running out of fuel transforms a star so profoundly, what happens when the sun begins to expand? Part 2. How the sun was born. From a cloud of darkness, long before the sun ignited, there was only a cold, silent cloud of gas and dust drifting through the Milky Way. But gravity has a way of gathering stillness into motion. As the cloud collapsed, it spun faster, tightening into a disk with a bright core at its heart. That glowing center, dense, hot, and trembling with pressure, would one day become the sun. Understanding its birth is the first step in understanding its fate. To imagine the sun before it existed is to imagine a space without warmth, a region of the galaxy dimmer than the faintest starlight, filled with sparse atoms of hydrogen and helium left over from the early universe. These atoms drifted for millions of years without direction, suspended in a quiet balance. Nothing in this cloud hinted that it would someday become the heart of a solar system. Yet, in the emptiness of space, equilibrium is fragile. All it takes is a nudge, a passing star, a distant shock wave from a supernova to disturb the calm. Astronomers believe that such a disturbance is what awakened our sun's ancestral cloud. Somewhere in our region of the Milky Way, a massive star may have exploded, sending ripples of compressed gas outward. As those ripples brushed the cloud that would one day be ours, they pressed the gas tighter together, creating tiny pockets of increased density. And in the universe, density is destiny. Wherever matter gathers, gravity strengthens. Wherever gravity strengthens, matter gathers faster. The collapse began quietly, imperceptibly, a slow inward drifting, like dust settling toward the center of a room. But gravity does not relent once it takes hold. As the OT cloud contracted, its particles fell closer together, heating through friction and compression. Even as the surrounding universe remained nearly absolute cold, the center of the cloud began to warm. And as it warmed, something else happened, something that shapes every star in the cosmos. The cloud began to spin. This rotation was not imposed from outside, but born from the subtle motions already present in the drifting gas. As the cloud shrank, its rotation sped up, a consequence of a simple rule of physics. When something contracts, it spins faster to conserve angular momentum. Astronomers see this same pattern in ice skaters who pull their arms inward, spinning faster with each centimeter they draw closer to their bodies. The cloud flattened into a swirling disk, thin, wide, and luminous at the center. Nearly all the mass gathered into this bright core, while the outer regions formed a vast rotating structure of dust and gas. This disk would eventually give rise to planets, moons, comets, and asteroids. But at its center, something more dramatic was unfolding: the birth of a star. The core grew denser and hotter with every passing millennium. Pressure mounted. Hydrogen atoms, once cool and slow-moving, now raced with immense speed, colliding constantly in a storm of heat and motion. But it was still not enough. The cloud's heart was bright from compression, not from fusion. For the sun to truly ignite, the core needed to reach a temperature of about 10 million degrees Celsius, a threshold that seemed impossibly distant in the early stages. Yet gravity continued its relentless work. It had no choice. It had only one direction to move: inward. As the collapse deepened, the disk around the forming sun began to organize itself. Dust grains collided gently at first, then more frequently, sticking together to form pebbles, then boulders, then objects kilometers across. These growing bodies would become the seeds of planets, long before the sun itself began to burn. In a way, the solar system began with darkness, countless collisions in the cold outskirts of a cloud, building the world we would one day call home. Meanwhile, the core of the collapsing cloud approached the critical point. The temperature soared. Pressure mounted beyond anything found naturally on Earth. Hydrogen atoms, forced so close that their repulsion could no longer keep them apart, began to fuse. And with that first spark of fusion, the sun was born. The ignition of a star is not an explosion, but a transition, a quiet victory over gravity. For millions of years, the core had been collapsing. Now, for the first time, there was an outward force strong enough to counteract the inward pull. Fusion pushed back against gravity, creating a delicate equilibrium that would define the sun's entire existence. The darkness faded. The core glowed fiercely. And light, for the first time, began its long journey outward. It would take tens of thousands of years for that light to reach the sun's surface. Inside a forming star, photons move through a labyrinth of dense plasma, scattering endlessly before escaping into open space. But once they finally emerged, the sun became what we know today, a stable, shining sphere of fusion-powered brilliance. The surrounding disk responded to this new light, heating and reshaping itself. Ice evaporated, dust melted. The solar wind, charged particles streaming from the sun, swept through the disk, pushing lighter materials outward. What remained closest to the newborn star were the heavier elements: rocks, metals, minerals. These would assemble into the inner planets: Mercury, Venus, Earth, and Mars. Farther out, beyond the warming influence of the sun, ices survived, forming the giant planets: Jupiter, Saturn, Uranus, Neptune, worlds shaped by cold and distance. Still farther, icy remnants became comets, drifting on orbits that would one day carry them back toward the sun in long, luminous arcs. The solar system's architecture is not random. It is the direct consequence of how the sun was born. But the story of that birth is not only about the physics of collapse, it is also about inheritance. The cloud that formed the sun was not pristine. It contained traces of older stars, elements like oxygen, carbon, silicon, and iron, forged in distant supernovae long before our solar system existed. Every heavy atom in your body came from those earlier generations of stars. The sun formed from their remnants, and in time, the sun will return its own remnants to the galaxy, continuing the cycle that shaped us. In a way, the sun is not a single event but the latest chapter in a cosmic lineage stretching back billions of years. The cloud that became the sun was only one of countless clouds drifting through the Milky Way, each one a cradle for future light. And just as the sun was shaped by the gravity of that cloud, it will one day shape the future clouds that follow. Understanding the sun's birth gives us insight into its fate. The same laws of gravity, pressure, and fusion that ignited it will one day bring about its transformation. The sun was born from collapse, and one day when its fuel's gone, it will collapse again, only to rise as something new, something smaller, something hotter. A white dwarf surrounded by the glowing remains of its outer layers. But that moment is far away. For now, the memory of the sun's birth is written in everything around us, in the orbits of planets, in the composition of Earth, in the warmth that reaches our skin every day. And as we move gently toward the next part of this story, one quiet question rises. If the sun was born through collapse and ignition, how does fusion maintain its delicate balance over billions of years? Part 3. Why hydrogen fusion keeps the sun in balance? At the sun's center, temperatures soar to millions of degrees, and atoms move so quickly that collisions become fusion. This fusion creates outward pressure strong, enough to counter the inward pull of gravity. The sun exists in this perfect stalemate, what astrophysicists call hydrostatic equilibrium. As long as hydrogen remains plentiful, this balance holds. But the moment that fuel begins to decline, gravity quietly starts to win. To understand why fusion and gravity balance so delicately, imagine the sun not as a glowing sphere, but as a constant negotiation between collapse and expansion. Gravity wants to pull every particle inward toward the core. It is relentless, patient, and absolute. Fusion, on the other hand, is the sun's answer to gravity, a counterforce born from heat, pressure, and motion. For 4.5 billion years, these two forces have matched one another perfectly, creating the illusion of stillness in a star that is anything but still. At the heart of the sun, hydrogen nuclei, protons, race through a plasma so hot that atoms cannot hold on to their electrons. In this environment, matter behaves like pure charge and pure energy. The nuclei repel each other naturally, each proton pushing against another through electromagnetic force. But at extreme temperatures, motion overcomes repulsion. Collisions become so violent that protons are pushed close enough for the strong nuclear force, the most powerful force known, to take over. When it does, fusion begins. The sun relies on a specific fusion pathway called the proton-proton chain. It is slow by cosmic standards, requiring millions of years for large-scale effects to become visible. And yet, on the human scale, millions of tons of hydrogen fuse every second. This slow but steady tempo is exactly why the sun lives so long. If fusion were faster, the sun would blaze brightly and burn out quickly. If it were slower, gravity would dominate and the star would collapse. Balance exists because nature has tuned the rates of fusion and pressure to match gravity so precisely that the sun's stability lasts for billions of years. The outward pressure created by fusion is not a single push, but a chain of events. Each fusion reaction releases energy in the form of gamma rays, high-energy photons born at the core. But these photons do not fly straight to the surface. Instead, they bounce from particle to particle in an endless random walk, scattering for tens of thousands of years before reaching the sun's outer layers. By the time they escape into space, they have lost energy, emerging as the visible light we know. This long journey is part of the sun's quiet balance. The outward flow of energy keeps the star inflated against gravity's inward pull. If energy production increases slightly, the sun expands, lowering the pressure in the core and slowing fusion. If it decreases, the sun contracts, raising core temperatures and speeding fusion. In this way, the sun self-regulates, gently, consistently, and with remarkable precision. It is one of nature's most elegant feedback loops, hydrostatic equilibrium, the balance between Gravity and pressure is not simply an idea. It is a physical requirement for a stable star. If gravity overwhelms pressure by even a small amount, the core compresses, heating up. Higher temperatures accelerate fusion, producing more pressure. If pressure grows too strong, the outer layers swell, cooling the core and reducing fusion again. The Sun lives between these extremes, constantly adjusting, constantly maintaining its shape. This balance is so stable that the Sun has remained nearly unchanged for billions of years. Its brightness, size, and temperature have drifted only slightly. Yet the conditions within the core are always evolving. As hydrogen fuses into helium, the composition of the Sun changes. Helium, heavier than hydrogen, sinks toward the center, gradually increasing the density of the core. Over millions of years, this accumulation subtly shifts the equilibrium. The core must contract slightly to maintain enough heat for fusion, and the surrounding regions must burn hydrogen more vigorously. This is why the Sun brightens slowly as it ages. It is not growing reckless, but adjusting. The outward pressure must strengthen to keep gravity at bay, and the only way to do that is for fusion to run a bit faster, a bit hotter, a bit more energetically than before. Over hundreds of millions of years, these small adjustments accumulate, raising the Sun's luminosity and altering the energy that reaches Earth. Despite these long-term changes, the Sun today remains firmly in equilibrium. Each second, 4 protons fuse into a single helium nucleus, releasing energy and reducing mass. This mass loss, about 4 million tons per second, is small compared to the Sun's immense total, but over eons, it shapes the star's evolution. Energy, after all, is not free. It comes from mass converted through fusion, slowly altering the Sun's internal structure. One of the most gentle yet profound truths of stellar physics is that stars spend the majority of their lives maintaining this balance. The Sun's main sequence phase, the period dominated by hydrogen fusion, accounts for nearly 90% of its lifetime. During this time, the Sun is neither collapsing nor expanding significantly. It shines steadily, providing the stable environment that allowed life to emerge on Earth. But even during this long period of stability, signs of future change are written into the Sun's behavior. Deep in the core, helium continues to accumulate. This helium does not fuse, not yet. It simply sits, adding weight to the center. With each passing million years, the core becomes slightly hotter and denser. The outer layers respond by expanding subtly. The Sun is brighter today than it was when the first oceans formed, brighter than it was when the first forests grew, brighter even than it was when the first humans walked the Earth. Someday, the helium core will become so massive that hydrogen fusion in the outer layers will no longer support equilibrium. At that moment, gravity will begin to tighten its hold. The Sun's internal pressure will no longer be enough to oppose collapse. The core will contract rapidly, heating to new extremes. And with that sudden rise in temperature, a rise so rapid it defies our ordinary sense of time, the Sun will ignite helium fusion, entering a new and unstable chapter of its life. But that is far in the future. For now, the Sun remains in the serene midpoint of its existence, held together by a balance of forces so perfect we rarely notice how extraordinary it is. Every sunrise is a quiet testament to the equilibrium between gravity and fusion, a balance sustained in the heart of a star that has burned longer than any living species on Earth has existed. The Sun's calmness is not stillness. It is the outcome of countless collisions, endless motion, and an intricate interplay of physical laws. It is a star in constant tension with itself, held steady by the very energy that tries to tear it apart. This is why hydrogen fusion keeps the Sun in balance, not because fusion is gentle, but because it is precisely enough. Not because gravity is weak, but because fusion is strong enough to oppose it. The Sun's life depends on this stalemate, this delicate truce between forces that otherwise could not coexist. And as we drift deeper into the Sun's long story, one question begins to rise softly from the core itself. If hydrogen fusion is the source of balance, what happens when the Sun's core fills with the helium that fusion leaves behind? Part 4. The slow rise of helium at the Sun's core. Every ray of sunlight begins with a single fusion event, and every fusion event leaves behind helium, the ash of a star's internal fire. Over billions of years, that helium has settled into the sun's center, forming a dense, growing core. The sun is still stable, still calm. But the buildup of helium is a warning written in light. One day, the core will become so packed that hydrogen can no longer burn where it once did. The story of this rising helium core is the story of a star slowly aging, not in sudden leaps, but in quiet, incremental shifts, too slow for any human lifetime to perceive. The sun does not show its age through dimming or cooling. Instead, it changes from the inside outward, its inner layers responding to the gentle but relentless accumulation of helium at the heart. This process is invisible to us, yet everything we know about stellar evolution tells us it is happening right now, quietly, constantly, inevitably. At the center of the sun, hydrogen fusion proceeds through the proton-proton chain, a series of reactions that convert hydrogen nuclei into helium. Each step in this chain releases energy, and each release adds to the outward pressure that counters gravity's inward pull. But while energy escapes to the surface, the helium remains. It does not burn, not yet. It cannot. The core is not hot enough for helium to undergo fusion. And so, atom by atom, reaction by reaction, the helium stays locked in place, forming a core that grows heavier and denser over time. Imagine the sun's interior as layers of different purposes. The outer layers carry light, the middle layers transport heat, but the core is where the sun's destiny is shaped. In the earliest days of the sun's life, the core was light and full of hydrogen. Fusion was simple. The pressure required to keep the star stable was easily maintained. But now, billions of years later, the core is no longer the same. Helium weighs it down, adding mass without adding energy. Gravity presses harder. The core contracts slightly to maintain the temperatures needed for fusion to continue in the surrounding shells. This contraction is slow. It is measured not in centuries or millennia, but in millions of years, and yet, inside the sun, contraction means heat. As the helium core becomes heavier, gravity squeezes it more tightly. This squeezing raises the temperature of the layers just outside the core, where hydrogen still exists. The hotter this region becomes, the faster hydrogen burns there. Fusion accelerates, and when fusion accelerates, the sun brightens. This is why the sun gradually grows more luminous as it ages. It is not because it is burning more fuel in total, but because it must burn fuel faster to balance the increasing weight of the helium core. This balance, this hydrostatic equilibrium, is always at risk of shifting. As the helium core grows, the pressure needed to maintain the sun's size grows as well. Fusion responds by increasing output. And so, the sunlight we see today is hotter, brighter, and more energetic than the light that fell on Earth when the first oceans formed. Yet the sun still appears unchanged to us. Its rising helium core produces no flares, no sudden changes, no visible signs in the sky. It continues to shine steadily, softly, with the same familiar warmth. But deep inside, the architecture is shifting. The sun we see now is not the sun that existed at its birth. Consider what happens as the helium core grows more massive. Helium, being heavier than hydrogen, sinks toward the center. The region where hydrogen once freely fused is pushed outward, forming a shell surrounding the core. Hydrogen fusion continues, but it is no longer happening in the same location. The core itself becomes inert, hot, yes, and under immense pressure, but unable to produce the energy that once sustained the sun's equilibrium. This shift in the location of fusion is one of the earliest hints that the sun is entering a new stage of its life cycle. The hydrogen-burning shell around the helium core becomes the sun's new power source, generating even more energy than the original core because it lies in a hotter and more compressed environment. But greater energy also means greater instability. The outer layers of the sun begin to expand slowly, their delicate balance disturbed. This early expansion is so gradual that it cannot be detected from Earth. Over the next billion years, the sun will grow slightly larger, slightly brighter, and slightly more diffuse. Earth's climate will respond long before the sun's structure becomes visibly different, yet the root cause will be the same: a helium core growing too dense for hydrogen to burn within it. The helium core itself is a strange place to imagine. Despite being unimaginably hot, far hotter than any environment on Earth, it is cold in a nuclear sense. There's not enough heat to fuse helium into heavier elements like carbon. This requires temperatures of around 100 million degrees Celsius, far above the sun's current central temperature. So the helium simply accumulates, forming a sphere of matter supported not by fusion, but by the quantum mechanical pressure of its particles. As the helium core grows, it becomes a kind of engine for change. Gravity compresses it further. Compression produces heat. Heat accelerates the surrounding hydrogen fusion, and that acceleration feeds the outer layers of the sun, making them expand ever so slightly with time. The sun is not bloating into a giant yet, but it is preparing for that transformation long before the change becomes dramatic. This gathering helium is more than a passive accumulation. It actively alters the sun's internal geometry. The temperature gradient steepens. The boundary between fusing and non-fusing regions sharpens, and the sun's convection patterns, its enormous internal currents, shift gradually to accommodate the altered distribution of mass. Every part of the sun must respond to the core's changing state. Even the sunlight that reaches Earth is carrying this message. Its increased brightness reflects deeper, invisible processes that have been unfolding for billions of years. The energy that warms your skin on a clear morning is a whisper from the sun's interior, saying that the core has changed, that the helium is rising, that the balance is evolving. And yet, despite this slow transformation, the sun remains serene. Hydrostatic equilibrium is still intact. For now, gravity and fusion are still evenly matched, but the helium core continues to grow. It will not shrink. It cannot. No process exists to remove it. It is the sun's inheritance, the inevitable product of its own shining. One day, long from now, the helium core will reach a mass and density where hydrogen can no longer fuse around it at the rate needed to support the sun. When that happens, gravity will take over completely. The core will contract violently, raising temperatures until helium itself ignites in a sudden explosive burst of fusion, a helium flash. This will mark the sun's transition into the red giant phase. But that event is still billions of years in the future. For now, the sun's core continues its quiet transformation, unchanged in appearance, but altered in essence. Every second, helium grows where hydrogen once burned. Every minute, the sun's interior becomes a little more compressed, a little hotter, a little closer to the moment when its peaceful balance gives way. And as we follow this slow, invisible rise of helium, another question emerges gently, like a ripple under the surface of light. What happens when the sun can no longer contain the changes building within it and begins its first visible expansion into a red giant? Part 5. Why the sun brightens as it ages. It seems strange that a star nearing the end of its life becomes brighter, not dimmer. Yet that is exactly what the sun is doing. As helium collects, the core contracts, heating the surrounding layers and causing hydrogen to burn faster. The sun shines about 30% brighter today than when Earth first formed. In the far future, this slow brightening will reshape our world long before the sun begins its final transformation. To understand why the sun brightens with age, imagine the star not as a constant, unchanging beacon, but as a living engine responding to subtle internal pressures. A star's brightness is not fixed. It is regulated by the delicate balance between gravity drawing matter inward and fusion pushing energy outward. And as the sun ages, that balance shifts, quietly at first, then with increasing insistence. What we see as a steady yellow glow is, on the inside, a complex conversation between collapsing layers and expanding heat. The key lies in the sun's changing core. Every second, hydrogen fuses into helium deep within its center. This helium is heavier and does not participate in fusion at the sun's current temperature. Instead, it settles inward, forming a growing dense core. As the core becomes richer in helium, it becomes less capable of producing energy. Hydrogen can no longer fuse as easily in the exact central region because the necessary fuel simply isn't there anymore. But the star cannot allow its energy output to fall. Gravity will not wait. So as helium accumulates, the sun adjusts. The core contracts, driven inward by gravity toward a more compact state. This contraction raises the temperature of the shell of hydrogen surrounding the core where fusion continues. The hotter that shell becomes, the faster hydrogen fuses. This faster fusion produces more energy, and more energy means more light. The sun brightens not because it is burning better fuel, but because it is straining to maintain its balance. This phenomenon is common among stars like ours. All stars on the main sequence, those in the steady hydrogen-burning phase of their lifetimes, brighten over time, some dramatically, some mildly. For the sun, the change is gradual. Over 4.6 billion years, its luminosity has increased by roughly a third. For billions of years more, the brightening will continue, and the pace will accelerate as the core becomes increasingly dominated by helium. It feels counterintuitive that aging could create more light. On Earth, age is often associated with depletion, fading, diminishing. But in stars, age means pressure. It means rising heat, squeezed layers, and growing intensity. The sun's increasing brightness is not a flourish of renewed strength. It is a sign that the internal balance is shifting toward instability. When scientists measure the sun's changing luminosity, they do not observe sudden leaps, but a slow, steady trend rooted in the physics of stellar structure. The sun's interior obeys well-understood principles. More mass in the core means higher gravity. Higher gravity means higher temperature. Higher temperature means faster fusion. This chain of cause and effect unfolds naturally over billions of years. At any moment, the sun seems unchanged, yet the light falling on Earth carries the imprint of a star, very slowly increasing its output. And this brightening has consequences. Long before the sun enters the red giant phase, Earth will feel the impact. Over the next few 100 million years, increased solar radiation will begin to evaporate oceans, shift climates, and alter the chemical balance of the atmosphere. But these changes are distant on human timescales, beyond any evolution that resembles our present world. Still, they remind us that even a star's subtle brightening has profound power. Inside the sun, the rising brightness also affects the layers that sit above the core. As energy production increases, the outer regions expand slightly. The sun becomes larger, though only barely, by a few percent at first. This expansion cools the surface somewhat, but not enough to offset the increasing luminosity. The surface temperature may drop a tiny amount, giving the sun a softer, slightly redder hue, but overall luminosity still grows. Stars are intricate systems. The outer layers respond to the inner temperature changes with their own cycles of expansion and rebalancing. This interplay of contraction and expansion, heating and cooling, is one reason stars like the sun can remain stable for so long. The sun is not a static sphere of gas, it is a self-regulating system, constantly adjusting to internal changes with remarkable precision. But each adjustment carries the sun a little further from the balance it once held with ease. Each correction increases the energy output. Each response pushes the star one step closer toward the moment when stability can no longer be maintained. One of the most fascinating aspects of the sun's brightening is just how slowly it unfolds. The Earth has orbited the sun 4.5 billion times, and in all that history, the sun's changes have been almost undetectable to any single observer. If humanity had lived beneath the ancient sun, we might have noticed a gentle dimness, a cooler glow. But the difference from year to year, or even century to century, is unmeasurable without sophisticated equipment. Stars do not rush through their lives, they drift. Because this brightening progresses over such vast stretches of time, its effects become deeply entwined with the evolution of planets. Earth's early atmosphere, oceans, and biological processes adapted to a sun that was much dimmer in the past, a sun that could not have warmed our world without additional greenhouse gases. The faint young sun paradox highlights this. Earth should have been frozen under a sun 30% less luminous, yet geological records show liquid water and thriving early life. Earth's own atmosphere compensated, maintaining temperatures suitable for biology. In the distant future, however, compensation becomes impossible. As the sun continues to brighten, Earth's systems will gradually falter. Increased radiation will accelerate weathering of rocks, reducing greenhouse gases. A runaway cycle will begin. Decreasing carbon dioxide reduces plant life declines, oxygen levels fall, oceans warm, evaporation rises, and heat escapes less efficiently. These changes set the stage for a slow but inevitable transformation long before the sun becomes a red giant. Yet even these far future consequences are part of the sun's natural path, a path shared by countless stars throughout the galaxy. The brightening is not a flaw or an anomaly. It is the hallmark of a main sequence star reaching maturity. The sun brightens because helium accumulates. Helium accumulates because hydrogen burns. Hydrogen burns because gravity compresses the core. Each step is the result of simple universal physics, unfolding on unimaginably long timescales. Even now, the sun is becoming more luminous each million years by a tiny but measurable fraction. This slow brightening will continue for another 5 billion years, until the hydrogen in the core is nearly exhausted. Only then will the sun's transformation accelerate, shining far brighter than today before expanding into the immense form of a red giant. When that moment arrives, the sun's luminosity will surpass anything we can comfortably imagine, thousands of times its current output. That stage will be brief compared to the long era of slow brightening, but it is rooted in the same core process we see right now. The sun adjusting itself to a changing interior, always striving to maintain equilibrium against gravity's pressure. Yet the sun we know today is still in its long, calm middle age, shining quietly, steadily, predictably. Its increasing brightness is real, but its pace is gentle. There is no rush, no sudden flare of instability, just the gradual shift of a star evolving along its destined path. This brightening is the sun's way of telling us where it is in its life cycle, a subtle hint that the fuel at its center is changing, that the core is becoming heavier, that the balance is beginning its long drift toward transformation. And as we follow this story deeper into the sun's fate, a new question begins to rise softly. What early signs will show us that the sun's old balance is slipping, and its first true changes into a red giant are beginning to unfold? Part 2. 6. The first signs of the sun's coming change. Hundreds of millions of years before the sun exhausts its fuel, small shifts will begin. The surface will swell, the temperature will fluctuate, solar winds will strengthen. These changes happen so slowly that no single generation could witness them. But in cosmic time, they mark the beginning of a star's long farewell. The sun will not transform suddenly. Stars rarely change in leaps. Instead, the first signs of its aging will emerge gradually, rippling through its structure with the patience of deep time. To us, these changes remain invisible. They unfold far too slowly for any human eye to detect. Yet astronomers, studying the physics of stellar evolution, can trace the quiet signals that will one day mark the sun's transition from steady middle age to unstable old age. One of the earliest signs will be the subtle expansion of the sun's outer layers. As the helium core grows denser and hotter, more energy is pushed outward through the sun's interior. The increased heat does not make the sun uniformly hotter. Instead, it causes the star's outer envelope to expand. The surface moves outward, increasing the sun's overall radius. This swelling is slight at first, no more than a whisper of change stretched across millions of years. But even tiny shifts in the sun size alter its brightness and temperature in complex ways. As the sun expands, its surface cools slightly. The star takes on a softer, more orange hue. This color shift is imperceptible from Earth today, but in the distant future, it will grow more pronounced. The sun's light will become a bit less white, a bit more golden, then gradually more amber. Long before it becomes a red giant, the sun will look subtly different, warmer in tone, broader in shape, a star beginning to loosen from its tightly bound form. Another early sign of the sun's transformation will be fluctuations in its magnetic activity. The solar cycle, which currently repeats every 11 years, may lengthen or become more irregular as the sun's interior changes. Magnetic fields are shaped by the movement of plasma inside the sun, and as the inner layers heat and expand, these flows shift. The sun's magnetic poles could flip more erratically. Sunspots might increase, decrease, or appear in unusual patterns. Solar storms, those immense eruptions of charged particles, could become stronger or more frequent. These storms, carried by the solar wind, will play a growing role in the sun's transformation. The solar wind, which currently streams outward through the solar system at all times, may intensify. As the sun produces more energy, more particles are flung outward into space. Over millions of years, this strengthened wind will begin stripping away material from the sun's outer layers, an early preview of the massive mass loss that will occur during its red giant phase. On Earth, these stronger winds would subtly reshape space weather. Auroras would stretch toward lower latitudes. Satellites would face increased radiation. The edges of the heliosphere, the bubble of influence around the sun, would shift outward, affecting the movements of comets and other small bodies in the outer solar system. But these effects, though interesting, are not the true markers of the sun's coming transformation. The real shifts happen where no human instrument can currently reach, in the deep interior, where the helium core is changing the sun from the inside outward. The core's contraction will become more pronounced. As gravity compresses it further, temperatures in the surrounding shell will continue to rise. Fusion in this hydrogen shell will accelerate, producing more energy than the earlier phases of the sun's life. This surplus energy has only one place to go, outward, and so the sun will brighten noticeably, far more dramatically than the slow 10% increase per billion years of earlier epochs. This accelerated brightening will push the sun into a new thermal rhythm. The outer layers will become more unstable. Convection, those gigantic currents of rising and falling plasma, will grow stronger. These currents will churn deeper into the sun than before, carrying heat outward more efficiently. The sun may begin to pulsate slightly, with small variations in size and brightness rippling across thousands of years. Though these pulsations are subtle, they are significant. They signal that the sun is starting to lose its grip on the delicate equilibrium it maintained for billions of years. Hydrostatic balance, gravity pulling inward, fusion pushing outward, will begin to wobble. Not dramatically, not suddenly, but enough that the sun will start drifting away from its long era of stability. For Earth, these early changes will have consequences long before the sun becomes a true giant. As the sun brightens, Earth's climate will shift. Increased radiation will warm the oceans, intensify weather patterns, and alter atmospheric chemistry. Over time, the runaway greenhouse effect that scientists predict will render Earth's surface uninhabitable will begin, not from any single cataclysm, but from the sun's gentle brightening over tens of millions of years. Yet even as the sun's changes reshape the solar system, the star itself will remain serene in its appearance. To a distant observer, the sun will still look like a typical middle-aged star. No dramatic flares, no sudden swelling, no signs of its future demise. Stars evolve so slowly that even their first signs of change are masked by the vastness of time. Only by studying the physics of many stars can astronomers piece together the sun's long-term fate. Among these internal changes, something else will begin to happen within the sun's core, something that marks the true beginning of the end. The helium core will reach a point where degeneracy pressure, a quantum mechanical force, begins to dominate its structure. This pressure does not come from heat or motion, but from the fundamental behavior of particles in extremely dense environments. When degeneracy pressure takes hold, the core no longer responds to temperature changes in the same way. It becomes less flexible, more rigid, and the surrounding layers begin burning hydrogen even more intensely to compensate for the core's unyielding mass. This shift marks a quiet threshold in the sun's evolution. It is still billions of years from becoming a red giant, but the foundation of that transformation is being set. Hydrogen fusion is increasingly confined to a shell around an inert, compact core. The sun's outer layers expand more easily, responding to the increased heat flowing outward. The brightening accelerates. The internal currents shift even further. From this point on, the sun's internal structure will drift steadily toward instability. The equilibrium between fusion and gravity becomes more fragile. The sun's magnetic behavior becomes more erratic. The radius swells. The solar wind strengthens again. All of these changes are slow, predictable, and unstoppable. Still, from Earth's perspective, the sun remains a gentle companion. Its light warms the land. Its heat sustains life. Its cycle continues. Humans, if they are still here, will see no sudden alarm, no drastic warning. The sun changes on timescales that dwarf every measure of human history. Civilizations rise and fall in the blink of a solar eye. Stars do not hurry. Yet the physics is clear. The first signs of the sun's coming change are not dramatic. They are quiet signals deep within the star, subtle shifts in its core, soft expansions in its outer layers, small variations in its magnetic rhythm. But those signals grow louder with time. They build over hundreds of millions of years. They form the overture to a transformation that will one day reshape the entire solar system. And as we drift forward into the next chapter of this unfolding story, one question begins to glow softly at the edge of the sun's future. When hydrogen burning finally falters at the core, what happens when the sun begins to expand in earnest, entering the vast and fiery stage we call the red giant phase? Part 7. When the sun expands into a red giant. When hydrogen finally thins at the core, gravity compresses the sun inward, raising temperatures until the outer layers respond by ballooning outward. The sun swells to hundreds of times its current size, its surface cooling to a deep red glow. This phase, the red giant, changes everything. Orbits shift, worlds scorch, and the sun reveals a new shape we have never seen before. The transformation into a red giant is not a sudden flare or violent explosion. It is the unfolding of processes that have been building for billions of years, waiting patiently for the moment when the sun's core can no longer burn hydrogen in the region where it once did. As that moment approaches, the internal balance that once kept the sun stable begins to unravel. Gravity wins the first battle, compressing the inert helium core. But in physics, no victory is one-sided. Compression heats the core, and that heat triggers a chain of reactions that force the sun to expand, slowly at first, then with unstoppable momentum. The red giant phase marks the sun's departure from the comfortable main sequence life it has known for eons. In the center, the helium core, now dense, compact, and dominated by quantum mechanical forces, is no longer fused. It has become a gravitational anchor pulling the surrounding layers inward. Hydrogen fusion continues, but only in a shell around the core. This shell burns hotter than the core ever did, generating far more energy than the sun's earlier phases. But the sun cannot remain the same size while producing this enormous flood of energy. The outer layers absorb more heat than they can contain. Pressure builds. And like a balloon inflating from within, the sun's outer envelope begins to stretch outward, pushed by the relentless influx of energy. At first, the change is subtle. A slight increase in the sun's radius, a soft reddening of its surface, a gentle drop in temperature. But as the hydrogen-burning shell intensifies, the sun's outer layers expand dramatically. Over millions of years, the sun grows into a star so large that Mercury and Venus vanish into its glow. Its surface stretches to engulf regions of space where planets once orbited in quiet circles. The sun, we know, a stable yellow star with a surface temperature of about 500 degrees Celsius, becomes unrecognizable. As it expands, the surface cools to around 3,000 degrees. Heat is still rising from the interior, but spread over a much larger surface area. It glows red instead of white. The sun becomes a vast swollen orb, a red giant whose beauty is matched only by its destructive potential. To imagine the sun as a red giant is to imagine a sky that would be unthinkable from Earth today. If Earth still existed when the Sun reached this stage, the Sun would dominate half the sky, appearing thousands of times larger than it does now. Its light would not be the crisp yellow of morning, but a deep ruddy glow, dimmer per unit area, yet overwhelmingly bright because of its sheer size. The world would be bathed in an eerie, endless sunset. But it is unlikely Earth will survive this stage intact. Models show that the Sun's radius will extend close to Earth's current orbit. Some calculations suggest the expanding Sun could engulf our planet entirely. Others propose that solar mass loss, caused by strong stellar winds, may push Earth's orbit outward enough that it escapes direct consumption. Yet even if Earth survives geometrically, it will not survive thermally. Long before the Sun's surface reaches Earth's orbit, the oceans will boil, the atmosphere will evaporate, and the surface will melt. Earth's familiar landscapes will be reduced to a glowing, molten world, stripped of its air and water, a silent witness to the Sun's vast transformation. The expanding Sun will also reshape the architecture of the entire solar system. As the Sun loses mass through intense stellar winds, its gravitational pull will weaken. Planets will drift outward in response. Their orbits will stretch and widen. Jupiter and Saturn may move into new regions of stability. The outer solar system, cold, distant, and quiet, may warm slightly as the Sun brightens, though not enough to awaken icy moons into Earth-like worlds. Still, the balance of the solar system will shift in ways impossible to imagine now, as gravitational bonds loosen and orbital distances increase. Inside the Sun, the red giant phase marks a period of profound instability. The outer layers, swollen to colossal proportions, become loosely bound. Convection, massive currents of plasma rising and falling, dominates the star's structure. These movements can create pulses in brightness as the Sun's surface swells and contracts in rippling cycles. The Sun becomes a dynamic, breathing world, its luminous surface shifting in slow, enormous patterns like waves across a cosmic ocean. During this phase, the Sun's mass loss becomes significant. The stellar wind grows stronger, hundreds or thousands of times stronger than it is today. Streams of particles escape into space, carrying away the Sun's material and contributing to the formation of a diffuse envelope surrounding the giant star. This envelope, illuminated by the Sun's growing brilliance, glows softly, hinting at the star's eventual evolution into a planetary nebula. But the red giant stage is not merely a period of destruction, it is also the prelude to a new kind of fusion. As the helium core contracts further, temperatures rise to around 100 million degrees Celsius. At this threshold, helium can finally fuse into carbon in a sudden and dramatic event known as the helium flash. This flash, although immense, is contained entirely within the Sun's core. From outside, it will appear as a quick but subtle adjustment. No explosion, no visible shock, just a restructuring of the Sun's internal engine. After the helium flash, the Sun stabilizes once again for a time, burning helium into carbon in a new equilibrium. But this phase is much shorter-lived than the hydrogen-burning main sequence. Helium burns faster, runs out sooner, and generates different patterns of energy. The Sun will contract slightly after the helium flash, becoming smaller and hotter. But soon enough, instability will return and a second expansion will follow. The Sun will oscillate through phases of brightness and swelling, shedding more and more of its outer layers. Gradually, the Sun's outer envelope will unravel entirely. Pulses of energy from the core will drive off shells of gas that drift into space, glowing with the colors of ionized elements. These shells, cast off in slow, beautiful waves, will create the planetary nebula that marks the Sun's final moment as a luminous giant. At the center of this nebula, the Sun's core will be exposed at last, a brilliant white-hot remnant called a white dwarf. But long before that final transformation, it is the red giant phase that reshapes everything the Sun ever touched. It is the phase that will melt worlds, alter orbits, and reveal the Sun as a swelling, breathing, ancient entity transitioning into the twilight of its life. Even now, billions of years before this transformation, the seeds of the red giant lie within the Sun's growing helium core. Every fusion reaction brings the sun closer to this moment. Every photon of light leaving the sun today carries the memory of changes happening deep within. And as we drift toward the next chapter of this story, one question emerges softly from the sun's expanding horizon. If the sun becomes a red giant, what does that mean for the fragile little world we call Earth? And will it be consumed, or will it escape into the widening darkness? Part 8. Will the sun consume the Earth? Astronomers study this question with quiet precision. As the sun expands, its atmosphere will extend outward into the inner solar system. Models suggest Earth may be engulfed, or perhaps drift outward as mass loss weakens the sun's gravity. Even if Earth escapes direct consumption, its oceans, air, and crust will not survive the rising heat. The red giant phase is not a violent explosion, but a steady, inescapable suffocation. To ask whether the sun will consume Earth is to step into one of the most delicate questions in stellar evolution, one woven with both scientific certainty and cosmic uncertainty. We know that the sun will transform dramatically. We know that its radius will reach into the orbit where Earth currently travels. We know that temperatures will soar, atmospheres will boil, and oceans will evaporate. But the exact choreography, the fine details of how the sun's mass loss, gravitational weakening, and expansion interact with Earth's orbit, is a complex dance governed by many subtle variables. Still, the broad outlines are clear. As the sun enters the red giant phase, it will lose a significant fraction of its mass. Today, the sun holds 99.8% of all mass in the solar system. Its gravitational dominance shapes every orbit. But during the red giant stage, strong stellar winds will carry away huge amounts of material. As this mass streams into space, the sun's gravitational grip on its planets loosens. Orbits widen, worlds drift. Earth's orbit will respond to this shift. As the sun loses mass, the distance between Earth and the sun will gradually increase. In theory, this outward drift might allow Earth to escape being physically engulfed by the swollen red giant. The planet could slip away from the sun's expanding radius, circling farther out in response to the lessened gravitational pull. But survival is not simply a matter of distance. Even if Earth remains outside, the sun's visible surface, the intense heat from the red giant, will transform the planet into a world utterly unlike the one we know. Before the sun even approaches Earth's orbit, the rising luminosity will boil away the oceans. Water vapor, once the source of clouds, rain, and rivers, will become a greenhouse gas trapping more and more heat. Temperatures will climb to hundreds of degrees. The atmosphere will grow thick with steam until sunlight breaks the molecules apart, allowing hydrogen to escape into space. Gradually, relentlessly, Earth will dry from the top down. The seas will disappear. The riverbeds will crack. The crust will heat to molten glow. Even mountains, which seem so permanent on human timescales, will soften under the unimaginable heat. The Earth will begin to resemble Mercury, airless, blistered, and scorched. The habitability that once defined our world will vanish long before the sun's surface comes near. But the question remains, will the sun actually touch Earth? Different simulations offer different answers. Some show the sun expanding just far enough to swallow our planet entirely. Others show Earth drifting outward just quickly enough to avoid direct engulfment. The challenge lies in modeling the chaotic exchange of energy and mass between the sun and its surroundings, interactions that unfold in slow spirals over billions of years. What we know is this: even if Earth escapes the sun's physical surface, it will not escape the sun's gravitational tides. As the sun expands, its outer layers become diffuse, extended, and unstable. These layers exert tidal forces on nearby planets, draining their orbital energy. Earth's orbit, weakened by these interactions, may shrink slightly even as the sun's mass loss tries to push it outward. It is a cosmic tug of war, not between solid objects, but between gravitation and gas, density and distance, orbital momentum and stellar evolution. Many astrophysicists believe that these tidal interactions will overtake the outward drift caused by mass loss. In their view, the sun's expanding atmosphere will act as a viscous drag, pulling Earth inward over hundreds of thousands of years, inch by inch, until finally the planet is consumed. The sun's outer layers, though thin, will still create friction. Earth will spiral toward the giant star, surrendering its orbital momentum into the sun's bloated envelope. If this happens, the engulfment will not be an explosive collision. The Earth will not fall into the sun like a stone into water. Instead, it will enter the sun slowly, almost gently, swallowed by gas hot enough to vaporize continents and core alike. The planet will dissolve into ions and become part of the sun itself. A world that once held oceans and forests, mountain ranges and cloud systems, civilizations and dreams will become a whisper of atoms among the many that make up the sun's swollen, dying layers. But there is another possibility. Some models suggest that Earth might move outward just fast enough to escape the drag of the sun's outer atmosphere. If so, Earth would remain outside the sun's glowing edge during the red giant peak. Yet this survival is survival only in name. The planet would be a barren rock, stripped of water, atmosphere, magnetosphere, and life. The Earth that remains would not be a world, but a relic. A molten sphere circling a dying star, drifting through a solar system completely transformed by the sun's expansion. In the outer solar system, objects once locked in cold darkness would warm slightly. Frozen moons and distant dwarf planets would feel the touch of sunlight, far brighter than anything they have known. But this warmth would be temporary. When the red giant phase ends, the sun's brightness will drop suddenly as it sheds its outer layers and contracts into a white dwarf. The outer worlds will freeze again. The solar system will be remade twice, first softened by too much heat, then stiffened by too little. In this cosmic reshaping, Earth's fate, engulfment or escape, matters little to the broader evolution of the solar system. What matters is the inevitability of transformation. The red giant sun represents the end of a long age of stability. Its expansion will erase everything familiar, regardless of whether the Earth vanishes into its glow or orbits just beyond it. Yet there is something strangely comforting in the predictability of this outcome. Stars of the sun's mass follow well-understood paths. Their lives are not chaotic or violent until the very end. They age slowly, grow steadily, and transform in ways that astronomers can map with remarkable precision. The sun is not failing, nor is it dying in the way living things die. It is evolving according to the physics that shaped every star like it. The question of whether the sun will consume Earth is not a question of catastrophe. It is a question of celestial geometry, mass, and motion. A question answered in billions of increments, each shift invisible, each moment quiet. There is no drama, no sudden calamity, only the long unfolding of natural laws. And as we drift deeper into the sun's story, another question emerges, softer, but no less profound. What happens inside the sun's core when hydrogen is gone and helium takes its place? What new fire awakens? And how does it briefly restore order before the final unraveling? Part 9. The strange new fusion that begins after hydrogen. When hydrogen at the core is gone, the sun begins fusing helium into carbon in a sudden, unstable burst called the helium flash. For a brief moment, the sun will shine with an intensity far beyond its ordinary light. Then, just as quickly, it will settle into a new equilibrium. But this reprieve is temporary. Helium burns fast, far faster than hydrogen, and the end that follows is irreversible. The moment hydrogen is exhausted in the core marks a turning point that no star of the sun's size can avoid. For billions of years, hydrogen fusion provided stability, creating the outward pressure that balanced gravity's inward pull. But once that fuel's gone at the center, the core contracts under its own weight. Temperatures soar, densities climb. The sun enters a regime unlike anything in its long, quiet middle age. At first, nothing appears outwardly dramatic. The sun is already swelled into a red giant by this stage, its outer layers barely held in place by the blazing shell of hydrogen burning around the helium core. But beneath that swollen surface, the core is collapsing into an environment where familiar physics begins to change. The particles inside the helium core, electrons, protons, and nuclei, are crushed together so tightly that classical laws give way to quantum rules. Pressure stops behaving like pressure. Heat stops behaving like heat. The core becomes a strange laboratory of density, temperature, and quantum mechanics unlike anything we experience on Earth. As the core collapses, its temperature climbs to around 100 million degrees Celsius, 10 times hotter than the core temperature during the Sun's main sequence life. This incredible heat is enough to allow helium nuclei, which repel each other more strongly than hydrogen nuclei do, to fuse. But fusion does not begin immediately. The core is in a degenerate state, meaning pressure comes not from temperature, but from the quantum behavior of electrons packed so tightly they resist further compression. In this degenerate matter, heat cannot expand the core to relieve pressure. The temperature rises without any accompanying expansion. This is the setup for the helium flash, a runaway event that occurs because the usual regulators of stellar stability are no longer functioning. When helium suddenly begins to fuse, the reaction is explosive in its intensity. Helium fuses through a process called the triple alpha reaction, where 3 helium nuclei combine to form a carbon nucleus. This reaction releases vast amounts of energy. In a non-degenerate core, the rising temperature would cause an expansion, and that expansion would cool the core, taming the reaction. But in a degenerate core, expansion does not immediately occur. Temperature rises faster and faster, accelerating fusion in a runaway loop. For a few moments measured in minutes within the core, though their effects unfold over hours, the Sun produces energy at a rate that defies comparison. Some estimates suggest the helium flash releases energy at 1 trillion times the Sun's normal luminosity. But this energy does not reach the surface. Instead, it lifts the degeneracy of the core, allowing it to expand. The expansion cools the core, halting the runaway reaction almost as quickly as it began. The Sun stabilizes into a new kind of star, a horizontal branch star, though that name applies more broadly to stars in clusters than to solitary stars like ours. For the Sun, it marks a calmer phase following the explosive ignition of helium fusion. The red giant contracts slightly, becoming smaller and hotter. Its luminosity decreases from its earlier peak, but remains far brighter than in the Sun's present life. Helium fusion begins in earnest. For the first time in its existence, the Sun is burning a new fuel, forging carbon and oxygen in its core through the triple alpha process and the subsequent reactions that combine carbon and helium to form oxygen. This stage is shorter-lived and more energetically demanding than the hydrogen-burning main sequence. Helium burns rapidly because the Sun must reach extreme temperatures for the fusion of heavier nuclei. These higher temperatures accelerate the reactions dramatically, consuming helium in a fraction of the time required for hydrogen fusion. While helium fusion stabilizes the core, the Sun's outer layers respond by contracting slightly. The red giant becomes less enormous, but still vast, tens of times larger than its current size. Its hue becomes a little whiter, its temperature a little higher. The Sun briefly enters a phase of renewed equilibrium, not as long-lasting or peaceful as its hydrogen-burning years, but stable enough to endure for tens or hundreds of millions of years. During this phase, some remarkable processes occur. The convective layers inside the Sun deepen, dredging material from the interior outward. Elements generated by fusion deep within the star, carbon, nitrogen, and others, are carried toward the surface. This dredge-up subtly alters the Sun's outer composition. In more massive stars, repeated dredge-ups create spectacular enrichments of heavier elements. In the Sun, the changes are modest but meaningful, marking the transport of newly forged matter to layers where, one day, it will be released into space. Meanwhile, the Sun continues to lose mass through strong stellar winds. The winds that began during the red giant stage persist, driven by the enormous luminosity and extended atmosphere of the aging star. The solar wind becomes a slow but unstoppable river of particles flowing outward, carrying away material that once belonged to the Sun's outer layers. This mass loss prepares the Sun for its eventual transformation into a planetary nebula. The helium-burning phase is brief compared to the Sun's long main sequence lifetime. While hydrogen fusion sustained the sun for more than 4 billion years, helium fusion will last only around 100 million years, roughly 1% as long. Helium is consumed far more quickly because the conditions required to fuse it are so extreme. Once the helium in the core is gone, a new phase of instability begins. When the helium runs out, the sun will no longer have a central energy source. The core, now composed primarily of carbon and oxygen ash, will contract again. But this time, the temperatures needed to fuse carbon are far beyond what a star of the sun size can achieve. Carbon fusion requires core temperatures of around 600 million degrees Celsius, 6 times hotter than the helium burning phase. Only stars several times more massive than the sun can reach such extremes. The sun will never ignite carbon, it will never fuse oxygen, its core will never burn again. Instead, the sun will begin another period of shell burning. Hydrogen will still fuse in an outer shell, and helium will fuse in a shell just outside the growing carbon-oxygen core. This dual shell burning is unstable and induces enormous pulsations. The sun's outer layers will swell again, larger than ever before. The star will re-enter a red giant-like state, but this time the expansion will be even more dramatic. The sun may reach a radius more than 100 times its present size, extending well beyond Earth's orbit. The star's luminosity will spike once more, its outer layers will grow increasingly fragile, held only loosely by gravity as they are pushed outward by intense radiation pressure. Pulses from the interior will drive waves through the sun's envelope, casting off shells of gas. These shells, illuminated by the dying core, will drift outward like cosmic veils, marking the sun's slow unraveling. Eventually, the sun's atmosphere will peel away entirely. What remains will be the exposed carbon-oxygen core, a white dwarf glowing fiercely at first, then fading over trillions of years. But the path to that quiet remnant begins with the helium flash, the moment when the sun burns a new fuel, briefly stabilizes, and then steps into the final stages of its life. And as we drift forward in this long narrative of stellar aging, one question rises like a soft pulse from the dying core. How does a star that once burned so brightly shed its entire outer shell, and what does that transformation look like in the darkness of space? Part 10. How the sun sheds its outer layers into space. As the sun grows unstable, deep pulses of energy lift its outer layers into space. Over tens of thousands of years, the sun will release enormous shells of gas, drifting outward like cosmic petals. These layers, once part of the sun itself, will eventually glow, lit by the hot remnant at the center, forming what astronomers call a planetary nebula. The unraveling of a star does not happen in a single moment. It is not an explosion, not a sudden severing of the sun from its outer layers. Instead, it unfolds in a quiet series of breaths, slow, rhythmic, and immense. Long after the helium flash ignites and then burns itself toward exhaustion, the sun enters a phase of profound instability. The core contracts, the outer envelope reacts, and the star begins to pulse. Each pulse is vast beyond our imagination, stretching across millions of kilometers of plasma. Yet these pulses rise and fall over periods that feel almost unhurried, not seconds but years, not years but centuries. The sun swells outward, then settles inward, then swells again, each cycle moving energy through its immense body like a tide. Deep within the sun, the source of this pulsing lies in the delicate layering of fusion shells. Hydrogen burns in one shell, helium in another. These shells sometimes ignite in irregular rhythms, heating the surrounding plasma in sudden waves. When enough heat builds up, the outer layers expand dramatically. But because these layers are now thin, cool, and weakly bound, the expansion carries them beyond the point where gravity can pull them back. They drift away, leaving the sun slightly lighter, slightly more exposed. This process repeats again and again. With every pulse, the sun exhales new material into space. At first, the mass loss is gentle, tenuous clouds of gas barely distinguishable from the solar wind. But as the sun approaches the end of its red giant phase, these gentle breaths become powerful. The star begins to shed mass at a rate millions of times greater than it does today. This is not a wind anymore. but a gale, a continuous outflow of gas that sweeps through the solar system, carrying atoms that once resided deep in the sun's interior. Hydrogen, helium, carbon, oxygen, elements forged through billions of years of fusion, are released into the cosmos. What was once the sun's outer atmosphere becomes a growing sphere of drifting gas, expanding far beyond the orbits of the planets. During this stage, the sun becomes what astronomers call an asymptotic giant branch star. Its outer envelope is so distended that it resembles a translucent bubble more than a solid surface. Convection currents stir its atmosphere like boiling water. These currents bring carbon and other fusion byproducts toward the surface, enriching the material that will soon escape into space. The sun becomes a forge not only of heat, but of heavy elements, materials that will later seed future generations of stars, planets, and possibly life itself. As the sun loses mass, its gravity weakens. The planets drift outward even more. The solar system becomes a looser, wider structure. Orbits stretch. The sun's hold on its worlds fades. Yet this growing separation does nothing to protect the inner planets from their fate. Long before the sun tears itself apart, the inner solar system has already been sterilized by heat. Still, above this destruction, the beauty of the sun's transformation is profound. The layers drifting outward do not scatter evenly. They form expanding shells, sometimes spherical, sometimes shaped into arcs or spirals by subtle magnetic fields or by the sun's own rotation. Some shells are dense, others are faint. Together, they build the architecture of what will become the planetary nebula, a grand luminous bubble of gas that glows in the last light of the dying sun. At this stage, the sun appears swollen and dim, wrapped in its own evaporating shroud. Much of its remaining light comes not from the visible surface, now tenuous and cool, but from the energy still flowing from the contracting core. Eventually, the outermost layers drift so far away that the sun can no longer heat them. They become cold, dark, expanding envelopes of matter that stretch into the emptiness of space. Then comes the moment that changes everything. The sun's core, now composed mainly of carbon and oxygen, contracts sharply as the last usable helium is consumed. This contraction raises its temperature enormously, not enough to ignite carbon fusion, but enough to become a fierce, radiant ember. The surface layers of the sun fall inward briefly, then detach completely. What remains is an exposed core, shining with a brilliance far greater than the bloated red giant that preceded it. This sudden exposure floods the surrounding gas with ultraviolet radiation. The drifting shells of material, once too cool and thick to glow, suddenly light up, fluorescing in brilliant colors. Hydrogen emits red light, oxygen glows green or blue, nitrogen adds shades of deep crimson. The sun, now a young white dwarf, illuminates the layers it shed, turning them into an expanding cloud of shimmering light. This glowing bubble is the planetary nebula. The name planetary nebula is a historical accident. Early astronomers observing these objects through small telescopes thought they resembled planets. In truth, they have nothing to do with planets at all. They are the luminous graves of stars like the sun, glowing shells of gas that will persist for tens of thousands of years before fading into the darkness of space. The planetary nebula stage is the sun's final act of radiance. From afar, it will appear as a delicate glowing ring or bubble surrounding a bright central point. Some planetary nebulae are perfectly round, others are shaped like butterflies, hourglasses, or twisted spirals. Their shapes depend on magnetic fields, stellar rotation, and the slow drifting of material during the star's last breaths. We do not yet know what shape the sun's nebula will take, but it will be beautiful. In this glowing cloud, the sun's past and future merge. The gas drifting outward is the sun's own substance, released back into the galaxy. Within it are atoms forged long ago, atoms that once helped shape the planets, the solar wind, and perhaps even the earliest molecules of Earth's oceans. Now those atoms return to the cosmic sea, ready to mix with interstellar gas clouds and become part of new stars someday. As the planetary nebula expands, it grows fainter. Over tens of thousands of years, the sun's hot core gradually cools. Its ultraviolet radiation weakens. The glowing shells lose energy, their colors fading. Eventually, the nebula dissipates entirely, merging with the thin interstellar medium that surrounds it. All that remains is the sun's core, a white dwarf no larger than Earth but containing half the mass of the sun. This white dwarf will shine brilliantly at first, then dim over billions of years. It will never fuse elements again. It will simply cool, becoming a dense, crystal-like object in the dark. But its legacy will drift among the stars. The material the sun sheds, those expanding shells, those cosmic petals, will scatter across light years. They may someday fuse into new clouds. They may be drawn into the formation of new suns. They may condense around young stars into new planets, moons, oceans, and atmospheres. The atoms that once belonged to our sun could one day sparkle as the light of another world. Yet that journey lies far beyond the boundaries of our solar system's story. For now, we stand at the edge of the sun's transformation and ask the next quiet question. What becomes of the core that remains, the white dwarf glowing at the heart of the nebula, and how does it enter the final eternal stillness of a star that has spent its fuel? Part 11. The birth of a white dwarf. At the heart of the expanding nebula, the sun's core remains, no longer burning, no longer growing, but still unimaginably hot. This exposed core becomes a white dwarf, a dense sphere of carbon and oxygen about the size of Earth. In this form, the sun's story shifts from fire to silence. The star that once gave light to billions of years of history becomes a lingering ember. The birth of a white dwarf is one of the quietest transformations in the universe. There is no explosion, no dramatic collapse, no rising shockwave sweeping through the darkness. Instead, the sun's core is revealed like a glowing coal uncovered when the last ashes fall away from an ancient fire. All the outer layers have been shed. The fusion has ceased. The nuclear furnace that once defined the sun's life has gone out. What remains is the innermost remnant, the star's final identity. For most of its existence, the sun's core was hidden from view. Photons born in that dense center took tens of thousands of years to reach the surface, scattering endlessly along the way. Nothing about the sun's appearance hinted at the structure hidden beneath. But when the last pulses of the red giant phase stripped the sun of its envelope, the core emerged, unshielded, bare, and brilliant. Its surface temperature soared to over 100,000 degrees Celsius. It shone with a fierce white-blue light, far hotter than the sun ever appeared in life, even though the energy now came not from fusion, but from residual heat held tightly within the core's collapsed structure. A white dwarf does not shine because it is burning. It shines because it remembers. Inside this remnant, matter is packed so tightly that ordinary atomic structure collapses. Electrons, no longer free to orbit their nuclei like they do in everyday atoms, are pressed into a state known as electron degeneracy. It is a strange condition where pressure no longer depends on temperature. The star remains stable not because of heat or fusion, but because quantum mechanics forbids its particles from being squeezed any closer together. This degenerate matter gives the white dwarf its extraordinary density. A spoonful of its material would weigh as much as a mountain on Earth. Its surface gravity is more than 100,000 times stronger than the gravity you feel right now. If you were somehow able to hover above a white dwarf, protected from temperatures that would vaporize any known material, you would see a surface smooth and bright, glowing with a ghost-like luminescence as heat radiates away into the emptiness of space. The sun, in this form, is no longer a star in the traditional sense. It is a stellar remnant, a memory of its former self, holding only the carbon and oxygen formed during its helium-burning phase. Everything lighter has drifted away into the nebula. Everything heavier belongs to stars far larger, far hotter, and far more violent than the sun could ever become. Yet despite its small size, the white dwarf is monumental in its story. It represents the sun stripped of everything external, reduced to the dense core that once held the pressure of fusion against gravity's pull. For billions of years, that core fueled warmth, light, seasons, and life. Now it rests, cooling slowly, its fate no longer shaped by nuclear reactions, but by the quiet mathematics of thermodynamics. Cooling is the white dwarf's final journey. At first, the temperature is so high that the remnant radiates intensely. The surrounding nebula glows vividly, illuminated by ultraviolet light from the newborn white dwarf. This is the moment when the planetary nebula blooms at its brightest, the dying star lighting the petals of gas it once cast off. But over time, the white dwarf cools. The glow of the nebula fades. The gas disperses into the interstellar medium. What began as a luminous, colorful bubble becomes a faint ghost of light, then disappears entirely, leaving only the white dwarf alone in the void. As the sun cools across millions of years, it transitions through shades of white and blue to yellow and red, eventually dimming into a faint ember. But this cooling is slow, so slow that the universe itself may not last long enough to witness the sun's final stage. Over trillions of years, the white dwarf will cool to the point where it no longer emits visible light. It will become a black dwarf, a theoretical object, for none yet exist, because the universe is not old enough for any white dwarf to have cooled that far. Yet the journey to becoming a black dwarf is measured not in epochs, but in cosmic eternities. Even as the white dwarf cools, something remarkable happens within it. As it loses heat, the atoms in its lattice-like structure begin to organize, forming crystalline regions. Over time, the entire remnant will solidify into a roughly Earth-sized sphere of carbon and oxygen crystal. In essence, the sun's remains will become a cosmic diamond, shining faintly with the residual energy of its long cooling. This crystallization is one of the most poetic truths of stellar evolution. The sun, after spending its life radiating light and warmth, will end as a frozen diamond-like core drifting through the galaxy. But long before that cold fate, the white dwarf stage itself shapes the space around it. Although it no longer produces strong stellar winds, its gravity still influences the remnant planets and asteroids that survived the red giant phase. Some worlds will have drifted outward during the sun's mass loss, others will have been swallowed completely. But a few distant objects, icy bodies in the outer solar system, may continue orbiting the white dwarf for billions or even trillions of years. Over time, these objects could drift inward due to gravitational interactions with passing stars or interstellar clouds. If they approach too closely, they may be torn apart by the white dwarf's intense tides, forming rings of dust around the remnant star. Many white dwarfs observed across the galaxy bear these dusty signatures, evidence of ancient planetary systems falling apart and settling into new forms. Our sun, too, may end its life surrounded by a thin disk of debris, the last remnants of comets, asteroids, or even outer planets pulled inward by the slow flow of time. In this quiet, dim environment, the story of the solar system continues long after the sun's brightness has faded. But in the largest view, the birth of the white dwarf is the moment when the sun's journey shifts from energy to memory. No longer a generator of light, it becomes a vessel of what once was, a relic holding the chemical and thermal imprint of a star's long, luminous life. The white dwarf is the sun stripped to essence, condensed into a final, still-burning truth that even stars, with all their brilliance, eventually settle into silence. And as we drift toward the next chapter of this cosmic story, a new question gently rises from the cooling ember at the center of the nebula. What does it mean for a star to glow without burning? How does a white dwarf shine? And why does its fading take longer than all of human history combined? Part 12. Why a white dwarf glows without burning. A white dwarf does not shine because of fusion. It shines because of memory, the stored heat of the sun's long life slowly escaping into space. No new energy is created. The glow is simply the last warmth of a star cooling over trillions of years. It is the quietest form a sun can take, bright, dense, silent. When the sun becomes a white dwarf, every part of its radiance shifts from the violence of fusion to the gentleness of cooling. It is the first time in more than 10 billion years that the sun will shine without making any new energy at all. The nuclear furnace has gone out. The core has settled into its final shape. The bright, exposed remnant radiates not because it is alive, but because it is still warm from the life it once had. This is a kind of glow that comes not from fire, but from the deep physics of heat itself. A white dwarf is the leftover ember of a star, and like any ember, it releases energy, simply because it is no longer able to keep that energy inside. In the earliest stages of its white dwarf existence, the sun will shine fiercely. The newly exposed core will be unimaginably hot, hundreds of thousands of degrees at its surface, hotter than any temperature it ever reached during its main sequence lifetime. But this heat comes from compression, not fusion. During the sun's final contractions, gravitational energy was converted into thermal energy. The collapsing core became a pressure-cooked sphere of degenerate matter brimming with stored heat. Once that heat is trapped inside a structure the size of Earth but with half the sun's mass, the only thing the remnant can do is release it slowly into space. This slow release is why the cooling is so extraordinarily drawn out. A white dwarf has a vast amount of stored thermal energy, but only a small surface area from which to radiate it. The cooling is like trying to drain an ocean through a pinhole. The process takes billions, trillions, even quadrillions of years. It is one of the slowest transformations in the universe. Yet the physics of a white dwarf's glow is stranger and more beautiful than a simple ember cooling. The material inside the white dwarf behaves in ways that do not exist in ordinary states of matter. The core is composed of carbon and oxygen nuclei, suspended in a sea of electrons so densely packed that quantum mechanics, not classical physics, dictates their arrangement. The electrons form a degenerate gas, an exotic state of matter where pressure does not depend on temperature. This means that as the white dwarf cools, it does not shrink. It does not collapse further. It does not change its internal structure. It simply cools steadily, gradually, like a star that has finally come to rest. Because the white dwarf is not supported by heat, its cooling does not trigger any further collapse into a neutron star or black hole. Only far more massive stars take those violent paths. The sun, being modest in mass, avoids the extremes and settles into its quiet, dense state. Over millions of years, the sun's white dwarf form will begin to dim. Its brilliant blue-white glow will fade to softer shades. The surrounding planetary nebula, once illuminated by its ultraviolet radiation, will disperse into space. The nebula will vanish long before the white dwarf itself stops shining. Without that glowing shell, the white dwarf will appear alone, an isolated point of light in the darkening solar system. Once bright, it will gradually shift into a faintly luminous sphere. Its cooling follows a predictable sequence: white to yellow, yellow to red, red to near black. But even as its light weakens, the white dwarf remains incredibly hot compared to anything on Earth. It will take billions of years just to cool from its initial state to temperatures of a few thousand degrees. Over that time, the white dwarf's surface will become more crystalline as atoms slowly settle into an ordered lattice. This crystallization is one of the most profound secrets of white dwarfs. Astronomers studying older white dwarfs have found evidence that their interiors harden over time, turning into crystal-like structures stretching across thousands of kilometers. As the sun's remnant cools, it too will solidify, beginning with its center and gradually expanding outward. The sun, once a sphere of gas, then a raging furnace, then a pulsing red giant, will eventually become a solid diamond-like object in space. But the glow that remains during this long transformation still comes from heat alone. There is no internal combustion, no fusion reaction renewing the light. Every photon that leaves the white dwarf is a photon of memory, heat stored during the sun's life, now migrating outward into the void. This quiet glow will cast soft light on the remnants of the solar system. The surviving outer planets, if any still orbit the white dwarf after trillions of years of gravitational nudges from passing stars, will circle a faint ember instead of a blazing sun. Moons of these planets, once frozen solid, might briefly reflect the dim light, Asteroids will continue their slow orbits, occasionally drifting inward. If any object wanders too close, the white dwarf's immense gravity can tear it apart, creating rings of dust that glow faintly in the residual heat. We see this around other white dwarfs today, ghostly disks of pulverized worlds that spiraled inward and were shredded by tidal forces. These dusty rings tell the story of planetary systems long past their prime, still interacting with the remnant star. Eventually, the Sun may have such a ring, or it may not. The long future of the solar system is filled with uncertainties. Small gravitational tugs from distant stars, or even the galactic tide, could reshape the trajectories of planets and comets over unimaginable spans of time. But the white dwarf at the center will remain, cooling, dimming, remembering. The timeline for this cooling stretches longer than the current age of the universe. The Sun will still be glowing faintly when the Milky Way has merged with Andromeda. It will still be glowing when new stars are born from clouds of gas that don't yet exist. It may still be glowing when planets form around stars that have not yet emerged, in regions of the galaxy that have not yet coalesced. After trillions of years, far beyond the lifespan of galaxies, far beyond the era of starlight, the white dwarf will cool to a point where its glow becomes undetectable. At that moment, it becomes what astronomers call a black dwarf, a cold, dark sphere of crystallized carbon and oxygen. These objects are theoretical because the universe is too young for any white dwarf to have cooled enough to become one. But in the distant future, the Sun will join this silent class of stellar remnants. A black dwarf does not shine, it does not burn, it simply exists, holding the final frozen shape of the ASB star it once was. But before the Sun fades entirely into that darkness, its white dwarf phase stands as the final luminous chapter, a long farewell written not in fusion, but in the slow release of ancient heat. And as we drift into the next part of this story, one last quiet question rises from the cooling ember. What happens after the final glow disappears? What does the end of a star look like when even memory has gone cold? Part 13. How the Sun's death creates worlds beyond ours. The gas the Sun sheds will drift outward, mixing with the galaxy. Someday, far from now, that material may help form new stars, new planets, new environments capable of life. In this way, the Sun's death is not an ending, but a redistribution, a return of matter to the cosmic cycle that created us in the first place. In the quiet after a star's passing, the universe does something remarkable. It does not let the star's remains vanish. It does not allow the materials forged over billions of years to simply dissolve or disappear. Instead, gravity, radiation, and time fold those materials back into the galaxy, weaving them into the next generation of worlds. When the Sun expels its outer layers and becomes a white dwarf, those drifting shells of gas will form a planetary nebula, a glowing bubble that burns briefly before fading into the larger darkness. But even when the nebula dissolves and the light dims, the story of that gas continues. Hydrogen, helium, carbon, oxygen, nitrogen, all the elements that the Sun carried with it, spread outward into interstellar space. Some drift into vast emptiness. Some mingle with the quiet dust between stars. Some find themselves drawn toward regions dense with molecular clouds. And these clouds, though dark and cold, are the galaxy's wombs. For millions of years, even billions, the material from the Sun will travel through the Milky Way. Although the particles disperse, they do not lose their identity. Every carbon atom cast off by the Sun is still carbon. Every oxygen atom remains oxygen, capable of forming water in the right environment. These atoms, reborn into the galactic sea, become part of a medium that is constantly flowing, constantly stirred by gravity, supernovae, and the orbital motion of the galaxy itself. Eventually, the Sun's remains may drift into a dense region of gas, a place where gravity begins to dominate. The molecular cloud thickens, dust gathers, turbulent motions compress pockets of gas, making some regions denser and colder. These clumps attract more material, and under their growing weight, they collapse inward. This collapse is the beginning of a new star's birth. In that process, the sun's atoms may become part of another stellar nursery. The carbon that once circulated through the sun's outer atmosphere could find itself in the heart of a dark cloud near the Orion Arm. Hydrogen that once fueled the sun's fusion may help ignite a new, young star. Oxygen and nitrogen may cool sections of the collapsing cloud, making it easier for gravity to pull the material inward. Even the dust, the tiny grains formed from heavier elements within the sun, can play a role. Dust grains are crucial for planet formation. They serve as the seeds around which larger structures grow. Icy coatings form on these grains in cold molecular clouds, creating sticky surfaces that allow them to clump together. Over millions of years, these clumps become pebbles, pebbles become rocks, and rocks become worlds. Somewhere in the distant future, a planet made partly from the sun's dust may orbit a new star. It might be rocky or icy, warm or cold, habitable or barren. It might carry water in its oceans or keep it locked beneath frozen crusts. It might form rings of ice, cores of iron, or atmospheres of methane. Whatever shape it takes, the atoms within it will have lived inside multiple generations of stars, including our own. This is the quiet truth of cosmic recycling. Stars like the sun do not disappear. They transform their material, and that material becomes the raw substance of future systems. Most of the heavy elements in the universe are created in massive stars, not stars like the sun. But the sun contributes something equally important: stability. Low-mass stars like the sun live long, steady lives, locking away elements for billions of years before releasing them gently. Their death is not a violent supernova, but a soft shedding of layers that carry precious carbon, oxygen, and nitrogen into the galaxy. These elements are essential for life. They are the backbone of organic molecules, the scaffolding of proteins, the breath of atmospheres. Even though the sun is not a powerhouse of heavy element production, the materials it releases are refined across its lifetime. They are the product of its fusion, its convection, and its circulatory cycles. They represent the oldest memories of our solar system, preserved in the sun's chemistry. The idea that the sun's death could help give birth to new planets may feel distant, even poetic, but astronomers see this cycle in action everywhere they look. In every direction, telescopes reveal stellar nurseries lit by the remains of earlier stars. Wisps of gas glow in the ultraviolet light of newborn suns. Dust lanes swirl into protoplanetary disks where new planets gather mass grain by grain. The universe is filled with the ghosts of ancient stars, stars that lived, transformed, and vanished long before the Earth formed. Our sun will one day join those ancestors. Its gas will diffuse into the interstellar medium. Its nebula will fade. Its carbon and oxygen will quietly blend with the galactic environment. The solar wind that once shaped the heliosphere will be replaced by the faint gravitational tug of a cooling white dwarf. And over long spans of time, so long that our species, our world, and even our galaxy's current shape will have changed, the sun's atoms will be swept into new structures. Some may become part of a future star. Some may become part of a comet in an alien system. Some may join the dust around a newborn planet, spinning around a star we cannot even imagine today. And perhaps in that distant future, one of those planets will orbit at just the right distance within a new star's habitable zone. Perhaps it will gather oceans, atmosphere, chemistry, and cycles. Perhaps life will arise there, built from the dust of stars that came long before. If that happens, then the sun's story will not simply end as a white dwarf cooling in the quiet. Its atoms will continue onward, helping shape new worlds, worlds that may host rivers, mountains, seasons, or perhaps minds capable of wondering where they came from. In this way, a star's death is never truly final. It is not an extinguishing. It is a graduation of matter back into the galaxy, a redistribution, a renewal. Even now, every atom in your body comes from stars that lived and died long before the sun was born. The calcium in your bones, the iron in your blood, the carbon in your cells, all were forged in ancient furnaces and released into space by stellar deaths of many kinds. You carry the legacy of stars within you, so will the beings, if any, who emerge on planets formed from the sun's remains. This is one of the most profound truths of astrophysics. Stars give themselves back to the universe. Their matter becomes the seeds of new creation. And so, as we drift softly toward the next chapter of this cosmic story, another question emerges, quiet and inevitable. What does it mean for our world, not just physically, but philosophically, to know that every atom returns to the stars and that the sun's death is part of an endless cosmic cycle that began long before us and will continue long after we're gone? Part 14. What will happen to the planets? After the sun is gone, with the sun reduced to a white dwarf, the solar system becomes a place of long shadows and drifting orbits. Planets that remain will circle a dim ember. Others may drift away entirely. Over trillions of years, gravitational encounters with passing stars could scatter the remnants of our system into the wider galaxy. For the first time since the solar system formed, the sun will no longer be its center in the emotional sense we know today. It will still be the gravitational anchor, small, dense, silently powerful, but its warmth will no longer shape the dance of worlds. Its brightness will no longer guide their skies. The solar system, once vibrant with light and movement, becomes a quiet arrangement of cold spheres circling a cooling core. Yet, even in this stillness, the planets continue their long evolution. When the sun sheds its outer layers during the red giant and planetary nebula phases, it loses a significant portion of its mass. This loss weakens the sun's gravitational pull. In response, the planets drift outward, expanding into new orbits. Some shift only, slightly. Others, especially the outer worlds, drift more noticeably. This process is slow, measured across millions of years, but its consequences reshape the system permanently. Mercury and Venus are gone by this stage. They were swallowed by the sun long before the white dwarf ever formed. Earth, though perhaps not engulfed, was stripped of everything that made it a world. Mars may remain, but it too will be frozen, its landscapes locked beneath a darkened sky. The gas giants survive the transformation. Jupiter and Saturn drift outward into wider orbits, carrying their moons with them. Uranus and Neptune, already cold and distant, move even farther into the darkness, becoming silent wanderers circling a star that no longer shines in any conventional sense. The dwarf planets, Pluto, Eris, Makemake, Haumea, continue their distant loops. The Kuiper belt remains, though stretched, and far beyond the Oort cloud, its trillions of icy bodies held loosely to the sun, begins to unravel as the sun's weakened gravity struggles to keep its grasp. For a time, perhaps billions of years, the solar system will remain intact in this new, dim form. The white dwarf's gravity is strong, even if its light has faded. The planets will circle smoothly, their orbits stable, predictable, unchanged on human timescales. But on cosmic timescales, stability is temporary. The system is now vulnerable to disturbances it once resisted easily. As the white dwarf cools, it becomes less luminous. Eventually, it will shine only in the infrared, then hardly at all. The planets will feel the loss of warmth, though by then life has long since vanished. Surface temperatures plummet, atmospheres freeze, oceans crystallize. Even the gas giants contract slightly as their internal heat, never replenished, slowly radiates away over eons. Yet the greatest changes are driven not by temperature, but by time, and by the galaxy itself. The Milky Way is not a static environment. Stars orbit its center in great spirals, passing near one another occasionally. Over billions of years, the sun's white dwarf form will experience close encounters with passing stars, some distant, some surprisingly near. A single close encounter, measured in light years, not miles, could subtly alter the orbits of the outer planets. A star passing within a few trillion kilometers might tug at Neptune's orbit, shift the path of Pluto, or disrupt the fragile Oort cloud entirely. Most encounters do nothing. A few create ripples. And across trillions of years, enough ripples accumulate to change everything. The Oort cloud will be the first to scatter. Passing stars will steal away its icy bodies, pulling them into new trajectories around the galaxy. Some will become long-period wanderers between stars. Others will be absorbed into the gravity wells of distant suns, and some may drift in the galactic medium for ages, never settling, never falling, simply traveling. After the Oort cloud dissolves, attention turns to the planets themselves. The outer planets are the most vulnerable. Their orbits, already expanded by the sun's mass loss, now lie in regions where the sun's gravity is weaker and where passing stars exert more influence. Over spans of time so long that even language struggles to measure them, quadrillions of years or more, gravitational nudges from the galaxy can push the planets into eccentric paths. Some may be flung outward, slowly drifting away until they escape the sun's pull entirely. Jupiter may leave first. Massive but not anchored by heat or radiation pressure, it could be dislodged by a distant stellar encounter. Saturn might follow, or swing into a new orbit so elliptical that its seasons last millions of years. Uranus and Neptune, already on the edge of the sun's influence, could be scattered through the inner regions of the galaxy. A world that once orbited in familiar rhythms could become a rogue planet, its sky forever dark, its temperature near absolute zero, moving through the galaxy without a star. The inner planets, with their tighter orbits, are safer for longer, but not forever. Even tiny shifts in momentum accumulate across trillion-year stretches. The white dwarf's gravity remains strong, but the galaxy is stronger. The solar system's architecture becomes a long, slow unwinding. Eventually, in the far future, after countless galactic rotations, one of two fates awaits the surviving planets. Either they drift away, leaving the white dwarf behind, or they fall inward. Falling inward is slower, rarer, and depends on complex interactions. But it can happen. If a passing star alters a planet's orbit enough, the planet could lose angular momentum and begin a gradual spiral toward the white dwarf. The final descent would be a long one, taking millions of years as tidal forces tear the world apart. Its fragments would form a glowing ring around the white dwarf, similar to the dusty disks observed around many white dwarfs today, rings made from the broken remains of ancient planets. It is possible that one day, long after Earth has been stripped to a bare rock, its fragments could drift inward toward the white dwarf sun. Tidal forces may break Earth apart stone by stone, atom by atom, leaving behind a faint debris disk that glows softly in the pale heat of the dying star. Or Earth may escape the solar system entirely, drifting into interstellar space as a wandering, lightless world. The solar system as we know it will not remain forever. It will stretch, loosen, and eventually dissolve into the galaxy. Every planet, every asteroid, every piece of debris will either be scattered into interstellar space or someday fall into the faint gravity of the white dwarf. This dissolution is not sudden, it is gentle, gradual, and inevitable, shaped by the flow of cosmic time far beyond human measure. It is part of the galaxy's long-term evolution as star systems form, live, drift, and eventually disperse. In a sense, the planets return to the galaxy just as the sun did. Their atoms, whether carried away in the form of dust, fragments, or whole worlds, rejoin the larger flow of matter. Nothing stays bound forever. Gravity gathers, gravity releases. Stars form, stars fade. Orbits tighten, orbits unravel. And through it all, the memory of the solar system remains, but in pieces scattered across the Milky Way, woven into new clouds, new stars, and new cycles of creation. As we drift toward the final part of this long, quiet journey, one last question glows softly at the edge of the fading solar system. What does the true end of the sun look like? After the white dwarf cools, after the nebula fades, after even the planets are gone, when all that remains is silence. Part 15. Why the sun's fate mirrors the fate of all stars like it. The sun is not unique in its life cycle. It is one of countless stars that follow the same arc, from collapse to ignition to expansion to cooling. This pattern is written into the physics of fusion, mass, and gravity. Understanding the sun's destiny means understanding how stars live, breathe, and fade throughout the universe. The story of our sun is, in many ways, the story of every star that makes the cosmos shine. If you were to drift through the Milky Way, slowly, quietly, with no urgency and no destination, you would see that the sun is only one expression of a much larger rhythm. Everywhere you look, in every direction, stars are born, stars mature, stars grow old, and stars die. Their lifetimes vary in length, brightness, and intensity, but their arcs follow the same underlying script written in the equations of physics long before the first galaxy ever formed. For stars like the sun, stars of moderate mass, steady temperature, and long lifespan, the pattern is especially clear. They glow not by will, but by balance. Gravity pulls inward, fusion pushes outward. As long as hydrogen remains in the core, this balance holds. This equilibrium is so stable that stars like the sun can shine for billions upon billions of years with almost no change in brightness. Their constancy makes worlds possible. Their longevity makes evolution possible. Their gentle light creates the conditions where chemistry can breathe, react, and eventually become life. And yet, the very process that keeps a star alive is the same one that ensures its eventual transformation. Every second, hydrogen atoms fuse into helium. Every fusion reaction deepens the core, graduates the star into a new phase of maturity. Every photon of light is a reminder that the fuel is slowly being used, that the star is quietly aging, even as it appears unchanging from the outside. This aging follows a trajectory that is consistent among stars like the sun. First comes the long, stable main sequence, the era when hydrogen fusion defines everything. For the sun, this phase will end only after roughly 10 billion years. Many stars of similar mass enjoy similarly long lives. But once their cores accumulate enough helium and their fusion zones shift outward, the same transformation occurs. They expand into red giants. Red giant phases are not rare. They are not dramatic exceptions. They are the natural consequence of a star exhausting its simplest fuel. All stars of roughly the sun's mass, or slightly larger or smaller, undergo this broad, swelling transformation. Their surfaces cool, their radii balloon, and the relationship between their cores and their envelopes changes fundamentally. Look across the sky, and you will see red giants glowing softly in the night, Aldebaran in Taurus, Arcturus in Boötes, Pollux in Gemini. These stars were once like the sun. They are now living through the same transition our sun will experience far in the future. They are glimpses into the sun's destiny, reminders that its path is not unusual but universal. After the red giant stage, stars of this size do something even more characteristic. They ignite helium in their cores. For the sun, this ignition will come in the form of a helium flash, a sudden powerful burst of fusion that stabilizes the core anew. Many stars undergo this flash. The physics of degenerate matter forces it, and the structure of their interiors ensures it. And, just like the sun, these stars will enjoy a brief period of renewed stability as they burn helium into carbon and oxygen. Yet, this reprieve is always temporary. Helium does not last long. Stars like the sun burn it quickly, consuming it in a fraction of the time required to burn hydrogen. And once the helium is gone, the star has no path to ignite carbon. It simply lacks the mass to compress its core to the necessary temperatures. Only stars many times larger can take that next step into deeper layers of fusion. So whether a star is slightly smaller than the sun or slightly larger, the next stage is the same. Instability. Shells of hydrogen and helium begin to fuse around an inert carbon-oxygen core. Pulsations build. The star expands again, larger this time, more luminous, more unstable. And gradually, inevitably, its outer layers escape into space. This shedding of material is not merely the sun's fate, it is the signature of every low to intermediate mass star approaching the end of its life. These stars release their envelopes into space, forming planetary nebulae, glowing shells that mark the transition from giant to remnant. These nebulae come in many shapes: circles, ellipses, jets, hourglasses, spirals. Their diversity is beautiful, but their causes follow the same physical rules: mass loss, ultraviolet radiation, expanding shells, and the exposed core illuminating the surrounding gas. Every planetary nebula is a star's last light painting itself into the darkness, and at the center of each nebula lies the next universal stage, the birth of a white dwarf. These remnants, dense, hot, shining without fusion, dot the galaxy like cosmic embers. More than 90% of all stars in the universe will eventually become white dwarfs. It is the most common endpoint of stellar evolution for stars between about 0.5 and 8 solar masses, a vast range that includes the majority of stars you can see with the naked eye. Even stars slightly smaller than the Sun, such as red dwarfs, will eventually produce white dwarfs. They burn far more slowly, so slowly that none have yet reached their final stages because the universe is not old enough. But their destiny is the same. They will contract into dense cooling remnants once their hydrogen supply finally runs out. Stars slightly larger than the Sun, up to about 8 times its mass, follow a similar path. Their red giant phases are more dramatic, their mass loss is more intense, their planetary nebulae are often brighter. But they too end as carbon-oxygen white dwarfs, cooling into silence over unimaginable timescales. This is the quiet truth of stellar evolution. Stars like the Sun do not explode. They do not collapse into neutron stars or black holes. They end gently, shedding their layers into the galaxy, leaving behind a core that cools forever. The fate of the Sun is simply one example of this vast, predictable pattern. In this sense, the Sun is not special. It is ordinary, one star among hundreds of billions, and yet, its ordinariness is what makes the story universal. Because stars like the Sun are common, the processes of their birth and death shape the galaxy profoundly. They distribute heavy elements, they create environments where planets can form, they provide stable energy for billions of years, allowing chemistry to evolve into biology. Most habitable planets in the universe likely orbit stars very similar to the Sun. To understand the Sun's fate, then, is to understand how the universe sustains itself. Every star that follows this quiet arc contributes to the richness of the galaxy. Their long lifespans allow planets to form and evolve. Their gentle deaths enrich the interstellar medium. Their remnants persist as markers of time, cooling slowly as the universe ages. The Sun's fate mirrors the fate of all stars like it, because the laws that govern fusion and gravity do not change from one star to another. They are universal. They are constant. They tie the fate of the Sun to the fate of distant stars thousands of light years away. When we study the Sun's life cycle, we are not studying a single isolated story. We are studying a pattern that repeats across the cosmos, shaping galaxies, shaping planetary systems, shaping the environments where life might emerge and thrive. And as we drift into the next and final chapter of this journey, a chapter where all these threads come together, one last quiet question glows. What does the Sun's long story mean for us, living briefly within its warmth, knowing that we are part of a cycle far older and larger than ourselves?